the next thing I want us to talk about is valid argument. So here's what we're going to talk about. So an argument is a set of statements called hypotheses, each of which is assumed to be true, and a statement C called our conclusion that is claimed to be deduced from our hypothesis. Okay? We say our argument is valid if and only if I have all of my hypotheses 1 and hypotheses 2 and ... no matter how many hypotheses I have, imply the correct conclusion. Okay? So let's take a look at a few examples. So here is one in sentences. So let's say if Marvin studies mathematics, then he is smart. Marvin is not smart, therefore Marvin does not study mathematics. That makes sense if we think about it, okay? But I want us to think of these as puzzles. So we need to make sure we know how to write them. So if Marvin studies mathematics, then he is smart. That's an implication. So this is P implies Q. Well, my conclusion is not Q. Therefore, that's what this that's what this like 3-period triangle is. Therefore, Marvin doesn't study mathematics. And we can use these, solve these by using a valid argument. So an argument is valid if the premise and the conclusion are related to each other in the right way to tell if the premise is true. Okay? So here's an argument that makes sense just like the math one, right? If Edith eats her vegetables, then she can have a cookie. Edith ate her vegetables, therefore she gets a cookie. I claim this argument is valid, but how do I know it's valid? Okay? Well, we can solve this using truth tables and using our equivalence laws. So let me show you an example. So one example is deduction. Okay? Let's let P denote Edith ate her vegetables and Q denote Edith can have a cookie. So I said if Edith eats her vegetables, then she can have a cookie. That would be P implies Q. Remember, if then is the implication symbol, this arrow. Edith ate her vegetables, so P I have. Therefore, Edith gets a cookie, Q, that's our conclusion. So let's take a look. I have P implies true. Edith can have a cookie. That doesn't mean she has to eat a cookie. So here I have, okay, Edith ate her vegetables. Can she get a cookie? Yes. Edith ate her vegetables. Can she have a cookie? Is false. True implies false. That's false. False implies true because she didn't eat her vegetables. Okay? We're really just looking at this first line here. I have true, true. That gives me a true. This is an example of modus ponens. So let's take a look at another example. So let's identify this argument as valid. P implies Q, not P implies Q, therefore Q. Okay? I want to look at the roles where P implies Q and not P and Q are true and figure out what's the truth value of Q. So I've got true, true, false, false, true, false, true, false, P implies true, true, false, true, true, not P, true, nope, not P, it's false. False, true, true. False implies true, that's true. False implies false, that's true. True implies true, that's true. True implies false, that's true. So let's take a look at where P implies Q and not P implies Q are true. That would be right here. What's the value of Q? True. So to solve our logical implications, we can restate them as rules of inference. So from P, we can conclude P and Q. That's an addition. From P and Q, we can include P. That's subtraction. From modus ponens, if I have P and P implies Q, I can get Q, and so on and so forth. So we can use these rules of influence to solve these arguments given hypotheses. So let's take a look at verifying modus ponens real quick. So I've got P, why does it not copy over? Darn it, I have P and P implies Q, that's going to give us not, that's going to give us Q. Let me double check that. So I have P and P implies Q, that gives us Q. All right, here it is in symbols. So it was right here, y'all. Jeez. So true, true, false, false, true, false, true, false. P implies Q. So P and P implies Q, that's true implies true, that's true. False and false is, false, true and false is false. False and true is false. False and true is false. This is where Q gives us a true value. So that implies that Q is true. So we're gonna go through some examples of our rules of inference. So I study mathematics or economics. If I have to take English, then I do not study economics. I do not study mathematics, therefore I do not have to take English. Okay? So let's write this out in symbols. Okay? Let's let P be I study mathematics, Q be I study economics, R be I have to take English, and our hypotheses are I study mathematics or economics, so that's going to be P or Q. If I have to take English, then I do not study economics, that's R implies not Q and not P, is my conclusion. Here are my hypotheses. Okay, therefore what we have to prove is, so these are my hypotheses, sorry. I do not have to take English, I do not study mathematics, that's our last hypothesis. Our conclusion is not R, which is therefore I do not have to take English, not R. So I need to prove P and or Q and R implies not Q and not P implies not R. Okay? And we're going to do this using our rules of inference. Okay? So let's take a look at this. So we're going to simplify. This statement right here. So if I have P and Q, that's our first hypothesis. R implies not Q and not P. What I need to do is I need to figure out a way to simplify two of these statements. Okay? So let's take a look at disjunctive syllogism. That's going to be step 4. What disjunctive syllogism says, if I have P or Q and not Q, we can conclude Q. So I'm left with Q by disjunctive syllogism. And you really have to keep track of your steps when it comes to solving these problems. Next, I have, let's take a look. And sometimes people will write like 1 and 3, saying that I performed a disjunctive syllogism on step hypothesis 1 and 3. So now I have 4 hypotheses because I simplified 1 and 3 down to 4. So now I have R implies not Q and Q. That's an example of modus tollens. I think I spelled that right. Modus tollens says if you have R implies not Q and Q, you can conclude not P. You can conclude not your first term, which is not R. Well, that's the conclusion we wanted to prove. So here on 2 and 4, we used modus tollens. And it's important you want to use every single one of your hypotheses. You have to use every single one of your hypotheses. Okay? So here's an example of it all worked out so you have it for reference. All right, so let's go through this example that I have. I have if Jill wins, then Jack loses. If Peter wins, then Paul loses. Jill wins or Peter wins, therefore Jack loses or Paul loses. So let's write this in logical symbols. Let's let P be Jill wins, Q be Jack loses, R be Peter wins, and S be Paul loses. So I have if Jill wins, then Jack loses. So that's P implies Q. I have if Peter wins, then Paul loses, which is R implies S. And I have Jill wins or Peter wins. So I have P or R. Therefore, my conclusion is Jack loses, which is Q, or Paul loses, which is S. So I have Q or S. This is the conclusion we're trying to reach. So for step number 4, I'm going to use constructive dilemma. And what constructive dilemma says is that if I have P implies Q and R implies S, this is the same as P or R implies Q or S. And this was constructive dilemma. Okay, so I used constructive dilemma on 1 and 2. Now I need to make sure I use 3 and 4. So if I have P or Q, and P or Q implies Q or S, well, if I have use modus tollens for this, modus potens on 3 and 4, this is like saying I have P implies Q and I'm given P. Well, that means our conclusion is Q, which in this case would be Q or S. So this is a valid argument. That's the last example I had for you guys, but if you would like more problems from the text worked out, send me a page and a number. I have a feeling I'm going to have to make a lot of videos of these, and that's totally okay, because it can take a little bit to understand. Don't go crazy like some of the people in Logicomics, and if you haven't read it yet, you really should.